All right, so here we are. We're at video 2 of Unit 5, and we're going to be talking about particle movement. We're going to talk about distance, displacement, and general position. And we're going to be using velocity for our first derivative and acceleration for our second derivative. So you're going to see that come back into play a lot here. A couple things to take note. If I'm talking about displacement of a particle, I'm talking about its result distance. So, for example, if you leave your house and you go to school, you're going to travel a particular distance. But if you leave your house, you go to school, and you come back home, your displacement would be zero because it's the total result. So, notice my displacement is that total area. So you going to school would be like a positive area, you coming home would be the negative area, and so they would cancel out and you'd have a displacement of zero. Position is pretty easy. We've been talking about position. If you want a position, you need an initial value, and then you need to add everything that changes um, about the distance you want to go. And you'll see that again in a little bit. The distance traveled, total distance traveled, that if we go back to the school scenario, if you start at home and you go to school and you come back, your total distance traveled would be these two things added together. So being positive versus being negative wouldn't be in effect here because we'd want to add both of these together. So to do that, we just do the absolute value, which is pretty normal to do something like that if you want total distance. So you're going to see these three different things come up quite a bit: finding position, finding displacement, and distance traveled. Notice absolute value, no absolute value. Okay, so we have the velocity of a particle is given, so you know the velocity. It might be a good reminder to show you this. X of t is always the position. V of t, if you'll remember, is velocity, which is the derivative of position. And acceleration is the derivative of the velocity, or you could think of it as the second derivative of the first position. So you should know those things, otherwise you're going to have some trouble relating them. Okay, so we have the velocity. We have x of 1 is -2. That means that's a position value. And we want a particle's position at time equals 3. The first thing I would do is write out what A is asking for. They want the position at 3. Well, if you want a position, you need an initial value. So we'll start at 1. And then we need everything we need from 1 to get to 3. So that would be from 1 to 3 of our velocity. Remember, it's always of the velocity. Why? Well, again, velocity times change in time would give you total distance, like meters or whatnot. Okay, so then x of 1 is -2 plus, now for this, if all I had was the graph, I mean the equation, I would have to graph this. So just a quick sketch here. If I plugged in, because you're doing the area, if I plugged in 1, I get 1. If I plug in 3, I get 5. And so the area here would be a trapezoid where I've got bases of 1 and 5, and the distance here is 2. So 1/2 base 1 plus base 2 times the height just results in an area of 6. So I've got -2 plus 6, or 4, for my total particle position. Okay, for part B, we want total distance. Total distance, remember, includes positive and negative stuff. So I want the total distance from 1 to 3. So that would be written as the absolute value of the velocity. Okay, so the good news is you've actually already done all this work. So you just want the absolute value of this area. Well, the second good news is your area already is all positive. So that would just stay 6. If there was some into the negative, you would just add those two things together rather than making what's below negative. All right, in the second example, we're going to be able to use our calculator, and we have the velocity of a particle given by this. Obviously, this is why we're using our calculator, and we know that x of 2 is 3, so that's an initial position. So let's start with part A. We want the position at 4. Let's write out what that looks like. I want the position at 4, and if I want the position, then I need a starting point, which I have, x of 2, and then I need the rest of the stuff from 2 to 4. So I'm going to do the integral of my velocity. Okay, so we can use our calculator. So here I go. I'm going to plug in x of 2, which they said was 3. So 3 plus my integral. Remember, I go to math, and that first category, I'm going to go to function integration, and then I just plug everybody in. So 2 to 4 my function is a little involved. So I need e to the, I've got my sine value. Now be careful because when you do a trig function, you have to close that off. So notice I close that off and then I move down, minus cos of x, close it off. Be careful, trust me, if you don't, that little mistake is going to change everything. Okay, you should also make sure you're in radians, which I am. Okay, so then I'm going to go ahead and hit enter. And so I end up with a position of 5.226. Okay, part B says that I want the total distance traveled by the particle. Total distance, remember, is the integral. I want to go from 0 to 5 of the absolute value. Displacement is when we do not do the absolute value. So I need this guy. Now, the cool thing is your calculator can do this and you don't have to worry because remember, some of your graph could be above the x-axis, some of it could be below, and you would want to add these two things together rather than having them cancel out. But we have an absolute value function in the calculator. So when we go to put this in, I'm going to do integral again, and this time I'm going from 0 to 5 though. And I want to do the absolute value. Now, there's places to get it, but I find the easiest is to go to catalog. So second, 0 is that catalog button. It's the first choice. So then it puts in my absolute value. And then I'm going to put all of that function back in, being very careful to close off parentheses when I need to. Okay. And sometimes it can take it a moment, especially with really complicated functions to find the integral. Your calculator's doing a lot of calculations. So don't panic. You can look up here. As long as that's moving, you're good. 4.677. Okay. Okay. On the next one, we have another calculator problem. Now we kind of have to decipher what's happening here. So we have a race car is traveling on a track. It has a velocity of 80 meters per second when the brakes are applied at time equals 0. Now, I'm going to stop for a second. If they're giving you a velocity, they're giving you at a particular time, that's a data point. So I would write that down. The velocity at time equals 0 is 80 meters per second. Okay. From time t equals 0 to the moment that the race car stops, the acceleration of the car is given by this. Oh, so in this problem, you're given acceleration. During the time period, how far does the car travel? So we want to know how far the car travels. That would be total distance. So, and we know it's going on a straight track, so we don't have to worry about any negatives, but you could do total distance traveled using the absolute value if you wanted. So basically, here's what I want. I want to know how far the car's traveled. So distance is the integral. I know I'm going from time equals 0. I don't know when it stops just yet, so that's a question mark. But again, technically, I want the absolute value, but again, I know this is going to be positive, so it won't matter. Okay, so I need some things. I need when the car stops, and I need the velocity function, which I don't have yet. So we'll have to look at what we do have and see how we can get those two things. So what I do have is the acceleration. So how would we go from the acceleration back to velocity? Because that's what I need. Yeah, I'd have to take the integral. So if I take the integral, that would give me velocity. I have to actually integrate this side. So this side, if I go up by a power and divide by 3, I get -2. Up by a power, I get t squared over 2. And then, plus c. Remember, you have to consider that you could have had a constant. So how can I solve for that constant? That's why they gave you this data point. So you know that when t is 0, so if I plug in 0 here, 0 here, the nice thing about that is this is 0, 0, and c, I should get out 80. So now you have your entire equation. So that's why they gave you all those critical values. Okay, so now all I need to do is plug that guy in here, except we need to know when to end our interval. Well, remember, we want to go from 0 to the moment when it stops. When it stops would be when the velocity is what? 0. So we need to figure that out. My suggestion, because this is a calculator, is to graph this. So I'm going to go in. I've already actually graphed it, put it as my y equals. So you would put this in as your y equals, and we're going to graph, and we're going to look for when it's 0. Well, clearly, I can see right here is when it's 0, but I can use my 0 function, second calc, 0. And then I can actually figure out what I want to look. I think I hit the wrong button. Hold on. Second calc 0. There we go. So then you can move your cursor, or you can say, oh, it looks like it's between 3 and 4. And you can type in 3, enter, 4, enter. And then it'll say guess, and you can say yes. And so it looks like it hits 0. It has a speed of 0 at about 3.339 seconds. That's when the velocity is 0. Okay, so now we know when to end our interval. So we're going to go from 0 to 3.339 of our velocity. Again, my car is only going in a positive direction, so I'm fine. But you could put the absolute value in, you'd get the same answer. So now we're just going to plug this in. Of course, we're going to use our calculator since we have it. That would be silly not to. So math integrate. I'm going to go from 0 this time to 3.339. Whoops. There we go. And because your function is already in as your y equals, you might as well just use it. So variables, y1. So whenever you're graphing it already, you probably already have it in there. All right, so we get 198.766. And because this is distance traveled and we were doing velocity times time, the time should cancel, leaving us just in meters. Because a lot of times they will want the units. All right, our last problem. So, okay, here we have a graph of the velocity, that's important, of a particle moving, and we know that the particle starts at y equals 3 when time equals 0. So this is, the particle starts as its position. This is a position, guys. So I would write down x of 0 equals 3, because as you can see over here at 0, I'm negative 2, because this is velocity. So just make sure you get the difference between what's being shown. So during what intervals of time is the acceleration positive? Well, if you're looking for when acceleration is positive and you have a graph of the velocity, remember, acceleration would be the derivative of this. So you're really looking for when the derivative of this graph is positive, or slope. Acceleration is slope of the velocity. So when is my slope positive? Here and here. So I'm positive from 0 to 2 and from 6 to 7. All right, what is the acceleration at time equals 4? So let's go over to time equals 4. So that would be this point, but I want acceleration, which is slope. So the slope through there is negative 1 over 1. So the acceleration at 4, and that's how I can write it, is negative 1. Now, does that mean the particle is speeding up or slowing down? This is from the previous unit. So speeding up versus slowing down, remember you have to look at both the acceleration and the velocity. My velocity at 4, which is this graph, is a positive number. If these two things are different, yes, it's slowing down. If they're the same, that's when we're speeding up. Okay, set up an integral to find displacement and not absolute value on the interval of 0 to 7. Okay, so I want 0 to 7 of v of t dt. So I just want the area from 0 to 7 of my graph. So I would find my total area from 0 all the way to 7. And when I do that, to save time, I've already done that ahead, I got 3. And they want units. So remember, even though you're doing the area on the velocity graph, the result when you do velocity times time is just in your single unit. So that my result is just 3 meters is my total displacement. Okay, for D, I want when the particle, where the particle is at 7. Where it is would be position. So I really want x of 7. But I need an initial value. Well, the only initial value you have, because remember, this is not the initial, this is not the position. The initial value you have is x of 0. So I'm going to go then from 0 to 7 of v of t dt. X of 0 is 3 plus the 3 we already know, so 6. Okay, E wants you to set up average velocity. Average velocity would literally be me just doing 1 divided by the width of my interval out in front of that total area from 0 to 7. So we already know that's 1/7, so it'd be a seventh of that total area, which is 3, so 3/7. And last but not least, total distance would be the absolute value. So I would want to make sure that I add any of the negatives as positives. So when I'm adding all this up, this would be positive, 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 and I got 7. All right, good luck with the problem sets, and I will see you in class.